All right. So in this video, we're going to talk about section 3.1, defining the derivative. Okay, and we're going to read the textbook and then just kind of make comments along the way. So in this section, we have 7 objectives. First, recognize the meaning of the tangent to a curve at a point. Okay. Calculate the slope of a tangent line. That's going to be called the derivative. Identify the derivative as the limit of a difference quotient. This is the main topic of this section. Calculate the derivative of a given function at a point. Okay, that's related to number 3. Describe the velocity as a rate of change and explain the difference between the average velocity and instantaneous velocity. And then finally, estimate the derivative from a table of values. Okay, nice. So let's go ahead and just read a little bit here. It says, now that we have both a conceptual understanding of a limit and the practical ability to compute limits, we have established the foundation for our study of calculus, the branch of mathematics in which we compute derivatives and integrals. Most mathematicians and historians agree that calculus was developed independently by the Englishman Isaac Newton and the German Gottfried Leibniz, whose images appear in figure 3.2. When we credit Newton and Leibniz with developing calculus, we are really referring to the fact that Newton and Leibniz were the first to understand the relationship between the derivative and the integral. Both of these we'll talk about, later in this reading. Both mathematicians benefited from the work of predecessors such as Barrow, Fermat, and Cavalieri. The initial relationship between the two mathematicians appears to have been amicable. However, in later years, a bitter controversy erupted over whose work took precedence. Although it seems likely that Newton did, indeed, arrive at the ideas behind calculus first, we are indebted to Leibniz for the notation that we commonly use today. All right, so we got a little bit of a drama here between Newton and Leibniz. Both major contributors to calculus. So tangent lines. What are tangent lines? Let's go ahead and read. We begin our study of calculus by revisiting the notion of secant lines and tangent lines. Recall that we use the slope of a secant line to a function at a point a f of a to estimate the rate of change, or the rate at which one variable changes in relation to another variable. We can obtain the slope of the secant by choosing a value of x near a and drawing a line through the points a f of a and x f of x, as shown in figure 3.3. Let's see, can we go to that? Yeah, too bad it's on the different page here. But here is a secant line. Basically, you want to try to find the rate of change at this point, a f of a. Well, what you do is you choose a point nearby a, let's just say, so x f of x, and just draw the line through those 2 points. The slope of that line is the average rate of change over the interval from a to x. Okay, and here's how you find the slope of that secant line. It's just the slope formula that you know from before applied to these 2 points. Okay, so here we have it. We can also calculate the slope of a secant line to a function at a value a by using this equation and replacing x with a plus h, where h is a value close to 0. We can then calculate the slope of the line through the points a f of a and a plus h f of a plus h. In this case, we find that the secant line has a slope given by the following difference quotient with increment h. So the slope of the secant line is found, again, through these 2 points, a f of a. And then instead of using x, a different notation is to use, instead of a as our x value, what's a value that's close to a? Well, that would be a plus h. A plus a little bit more. H is a value close to 0, so it's just a little bit more than a. And so the coordinates of that point are going to be a plus h, and then f of a plus h. The slope of the line through those 2 points is found by, this y value minus that y value, f of a plus h minus f of a. that's here on top, and then the x2 minus x1, and it reduces down to this part here. Okay. So 2 ways to compute the slope of a secant line. So definition, let f be a function defined on an interval I containing a. If x is not equal to a, is an I, then Q, defined to be the difference quotient, f of x minus f of a over x minus a, is a difference quotient. Okay, so basically it's just saying you can choose any x value inside of an interval close to the value a. Okay, and then we also define the difference quotient with increment h, defined this way. Okay, nice. These 2 expressions for calculating the slope of a secant line are illustrated in figure 3.3. We will see that each of these 2 methods for finding the slope of a secant line is a value. Depending on the setting, we can choose one or the other. The primary consideration in our choice usually depends on ease of calculation. Yeah, so what is, just saying, sometimes one is easier to calculate than the other. Both of them are useful. So that's why we present both of these slopes of secant lines. Okay, in figure 3.4, we see that as the x values of, as the values of x approach a, the slopes of the secant lines provide better estimates of the rate of change of the function at a. Furthermore, the secant lines themselves approach the tangent line to the function at a, which represents the limit of the secant lines. Similarly, 3.4b shows that as the values of h get closer to 0, the secant lines also approach the tangent line. The slope of the tangent line at a is the rate of change of the function at a, shown in figure 3.4c. Okay, so just to kind of mention, what was being said there, we already talked about the average rate of change over, a large-ish interval from a to x1. But if we want to know the instantaneous rate of change at a, what we really want is this red tangent line here. We want to know what is its slope. And so the way that we can use the green line, or the slope of a secant line, to approximate the slope of the red line is to instead choose a point not x1, but a point even closer to a. Let's say x2. The value x2 is closer to a, and so its slope, the slope of the blue line, more closely approximates the slope of the red line. And as we get closer and closer to a, the slope of the secant line will approximate the slope of the tangent line. Okay. So what we're going to do is, in order to get the slope of that tangent line, we are going to take the limit as x approaches a of that difference quotient that we talked about just a moment ago. The same thing can be done with the other formulation for this difference quotient with increment h. But how do we do it here? There's a slight difference. Well, remember we have 2 points or 2 x values, a and then a plus h1, some value h that's close to 0. Okay, well, the approximation is, okay here. But again, we want to get it to approximate this tangent line here in red. And so how can we do that? We can decrease the value of h, make h smaller so we get closer to a. And if you make h smaller, then you'll get, from the green line, if h decreases, you get this blue line, which more closely represents the slope of the red line, the slope of the tangent line. So here we're decreasing the value of h to get closer and closer to the tangent line. The secant lines approach the tangent line as h gets closer to a. So what do we do here? We need to take a limit, but this one here is as h approaches 0, as h gets infinitely small of this difference quotient with increment h, that is going to be exactly equal to the slope of the tangent line. And then here's a tangent line just by itself. Okay, nice. So let's just read the caption here, the figure 3.4. The secant lines approach the tangent line, shown in green, as the second point approaches the first. Okay, very good. And then there's all these little nice little things you can click on. So if you're reading the book, you can click on those and kind of play around with them. In figure 3.5, we show the graph of f of x equals the square root of x and a tangent line at 1, 1 in a series of tighter intervals about x equals 1. As the intervals become narrower, the graph of the function and its tangent line appear to coincide, making the values on the tangent line a good approximation to the values of the function for choices of x close to 1. In fact, the graph of f of x itself appears to be locally linear in the immediate vicinity of x equals 1. Okay, so what is this saying here? Just kind of talking about the usefulness of the tangent line. Let's start, with this upper left, picture here. You can see the tangent line is there in orange, right? And obviously it's not the same as this curve, the square root of x function. But if you look in that side of that rectangle and you zoom in close enough to it, if we zoom in, and I can actually zoom in, here, you see, well, you can't really tell much of a difference between the tangent line and the curve in this little circle that I've drawn here. So if you zoom in really close to that, that little portion there, you can see that the tangent line very well approximates the curve. And so if we wanted to approximate values of the function, the square root of x, we can use the line and figure out what values lie on this line, or find function values, approximations on the line, rather than using the square root function itself. Okay, so you zoom in close enough, and that's what they're showing here on this little rectangle here. You get a very good approximation of a nonlinear function using a linear function. And lines are very simple, for us. We've studied them a lot in the past, hopefully. And calculus is going to show us that we can use linear functions to approximate nonlinear functions in many cases. All right. Formally, we may define the tangent line to the graph of a function as follows. And basically, I'll read what it says, but it's just the tangent line. The slope of the tangent line is going to be equal to the limit of the difference quotient. Or if you want to use the other formulation, the slope of the tangent line equals the limit of the difference quotient with increment h. Okay, so let's read the definition. Let f of x be a function defined on an open interval containing a. The tangent line to f of x at a is the line passing through the point a f of a having slope m tangent, provided this limit exists. Equivalently, we may define the tangent line of f of x to a. The equation equivalently, we may define the tangent line to f of x at a to be the line passing through the point a f of a having slope m tangent, and it's the limit of the difference quotient with increment h, and the limit as h approaches 0, provided this limit exists. In some cases, the limit might not exist, and we'll have to do something different in those cases. Just as we have used two different expressions to define the slope of a secant line, we use two different forms to define the slope of a tangent line. In this text, we use both forms of the definition. As before, the choice of definition will depend on the setting, now that we have formally defined a tangent line to a function at a point. We can use this definition to find equations of tangent lines. Okay, so let's go ahead and find a tangent line. And we'll do this example here. It says, find the equation of the tangent of the line tangent to the graph of f of x equals x squared at x equals 3. And so I'll give a little brief graph here. And this is going to be just a little sketch. Of course, not accurate, very accurate at all. But, let's say this is 9, this is 3. We know what the x squared function looks like. And here we have a line with positive slope. This is the tangent line. It just grazes the function. And so how do we find the slope of this line, first of all? This is what we just talked about. The slope of this tangent line is going to be the limit as x approaches. Our value a here is 3 of f of x minus f of 3 divided by x minus 3. Okay. And so we plug in. Let me just shift this. I'll put this over here. Let's go ahead and plug everything in. What is f of x? F of x is just a function. That is x squared minus f of 3. What is f of 3? That's, we just plug in 3 into our function. Okay. Divided by x minus 3. And so we get x squared minus 9 divided by x minus 3. And this factors, and my notation here is horrible. What I should have done is, I'm getting a little lazy here. And this is not good, so let me go ahead and fix it and write down. I should write the limit here each time. I might get, deducted a point or something if I leave it off. We need to take this limit here. We can stop writing the limit once we actually, look for the limit as x approaches 3. If you do this mentally, you can plug in 3 into both the numerator and denominator at this point, and you'll get 0 over 0, which is an indeterminate form. And so we need to try to find some sort of other method to evaluate this limit. Now, that other method is using some sort of algebraic manipulation to reduce this. And we can use factoring. X squared minus 9 reduces to, or factors to x minus 3 times x plus 3 divided by x minus 3. And you can see that the x minus 3 factor would cancel out. And so we get the limit as x approaches 3 of x plus 3. Now we can use direct substitution, and we plug in our 3 in place of x. 3 plus 3 is 6. The slope then, notice this entire time we were trying to find the slope of the tangent line, is 6. If the slope is 6, and we know that the point that this line goes through is 3, 9, we can see it right there in the picture, then we can use all of this information here. The slope of this tangent line is 6. The point is 3, 9. This is our x and our y. And so I'll use the point slope form. Y minus y1 equals m times x minus x1. And so y minus 9 is equal to 6 times x minus 3. If we add 9 on both sides, then we get y is equal to 6x minus 18. And then we're adding 9 on both sides, so we get a plus 9 there. So y is equal to 6x minus 9. Now, does this look accurate? It looks like our picture is going to intersect the y-axis somewhere, below the x-axis. So it looks like we're going to get a negative value. And yeah, that's actually what this picture shows right here. Okay. I won't read this here. I am kind of short on time today. So we saw the solution. You can read through this solution here and see what they do exactly the same thing, basically. So we'll move on. Okay, it is good to use both formulations of the slope of a tangent line. So in example 3.2, it looks like they do it with the other definition of the tangent line slope. So let's see here. Let's go ahead and do that as well. So instead of using the limit that they, this limit formula here, f of x minus f of a, we'll use the other one. So let's go ahead and write it down. The limit as h approaches 0 of f of x plus h minus f of x divided by h. And in this case here, we're going to say x is equal to 3. Okay. And so we have the limit as h approaches 0 of f of 3 plus h minus f of 3 divided by h. Now we could ask ourselves, okay, what is f of 3 plus h? If f of x is x squared, then what is f of 3 plus h? That is 3 plus h squared. And if you multiply this out here, this is 3 plus h times 3 plus h, which gives us, we use the FOIL method here, or just distributive property. This is 9 plus 6h plus h squared. And so this is what we will replace f of 3 plus h with. F of 3 plus h is equal to this expression here. That will be put right here. F of 3 we calculated before. That was 3 squared, or 9. And so let's go ahead and plug that all in. We get the limit as h approaches 0 of 9 plus 6h plus h squared minus f of 3 is 3 squared. Yeah, I'll write it down as 3 squared divided by h. And so just a little note here, it is sometimes good to do, some scratch work, like f of 3 plus h. I don't want to plug it into the limit necessarily, because maybe it might take a few steps to figure out what that is, and that's what I did over here on the side. That way you don't have to write the limit a whole bunch of times. That can be done kind of on the side. Well, now you can see that 9 and minus 3 squared are opposites of each other, 9 minus 9. And so we can cancel those out. And so we get the limit as h approaches 0 of 6h plus h squared over h. We can see that there is a factor of h common in the denominator. So you factor out an h on both top and bottom. These will cancel each other out. And so we get the limit as h approaches 0 of 6 plus h. Now we can do the actual limit. If we let h go to 0, then we get 6 plus 0, or just 6. Notice that this entire time, this limit represents the slope of the tangent line. And so what we got is that the slope of the tangent line is equal to 6. That's exactly what we got before. We could find the equation of the line in the exact same way. I wonder if they redo it. No, they don't. Yeah. Yeah, so notice this way of doing it here results in the exact same answer. The slope of the tangent line is 6, and over here we said the slope of the tangent line was 6 as well. All right, very nice. All right, what if we have a different type of function? Sometimes they require different methods to simplify. And so this one here says, find the equation of the tangent line to the graph f of x equals 1 over x at x equals 2. So for this one, I won't find the equation of the tangent line, but I will find the slope. That's the new part. And then you should know how to find the equation of a line once you're given a slope and a point, right? So we'll probably find, maybe we'll just do it. Okay, so find the equation of the tangent line to the graph. So our function, I'll write it somewhere here, f of x is equal to 1 over x. I need to find the slope of the tangent line. So I'm going to use the limit as x approaches a of f of x minus f of a divided by x minus a. And so in this case, a, our value of a is equal to 2. This is that value that we're interested in, the x value that we're interested in, that is 2. And let me use a new page actually, so I can write both methods side by side. So we can see the difference in them. Okay, so what do we need to find? We need to find, well, we already have f of x, that's in there. A is equal to 2, and we need to find f of a. Sorry, yeah, f of a, which is f of 2. The limit as x approaches a, which is 2, is f of x minus f of 2 divided by x minus 2. Okay, so we need to find f of 2. Let's see how hard that is to find. 1 over 2, not too hard. Okay, so let's go ahead and plug everything in. The limit as x approaches 2 of f of x, that's 1 over x, minus f of 2, 1 over 2, is divided by x minus 2. And so how do we deal with this? Fractions inside of a fraction. We saw this on the homework. If you're in the class here, you know, you've seen complex fractions. And what we can do here is just multiply by the least common denominator. The least common denominator here is 2x. So we'll multiply by 2x on both the top and the bottom. And I'll show the step here because I think we didn't have too much time in class to talk about complex fractions, but 1 over x is going to be multiplied by 2x. 1/2 is going to be multiplied by 2x. And then x minus 2, that is also going to be multiplied by 2x, but maybe we'll just leave that without multiplying it. So let's go ahead and simplify the limit as x approaches 2 of what cancels on top here, this x with that x. And so we're left with a 2 in the first term. And then the 2's cancel in the second multiplication. So we have 2 minus x over x minus 2 times 2x. Okay. Well, x minus 2 and 2 minus x, those are actually exact opposites of each other, right? I'll write it down right here beside it. Negative x positive 2 is on top, and then x minus 2 is on the bottom with 2x. So you can factor a negative from the numerator. The limit as x approaches 2. I'll factor a negative and then get x minus 2 on top, x minus 2 on the bottom, and 2x. And notice if I cancel these two terms, or these two factors, I should say, then I get the limit as x approaches 2 of negative 1 over 2x. And now I can do direct substitution, and it will work. The limit as x approaches 2 is negative 1 over 2 times 2, or negative 1 over 4. Okay. So the slope of the tangent line, the slope that we're looking for is negative 1/4. Our x value was 2, the one that was given. The y value for that, when we plugged in that 2, we got 1/2. And so let's just find it. Using the point slope form, we get y minus y1 is equal to m times x minus x1. And so adding the 1/2 to the other side, and then distributing, we're going to get y equals negative 1/4 x plus 2/4 plus 1/2. And you know 2/4 is 1/2. So we get 1/2 plus 1/2, which is 1. Negative 1/4 x plus 1 is the equation of our line. Yeah, and I don't know if they even show all the steps there. That is the correct line though. All right. So, just another example on how to use the that limit definition for the slope of a tangent line. Just because it's so important, and I want to show the differences between the two, I'm going to show the slope of the tangent line again using the other limit definition. And so the limit definition is f of x plus h minus f of x divided by h. And so notice that here, okay, the function is still the same thing. The function f of x is equal to 1 over x. But here we use the x value equal to 2. We don't have an a. Here the only point of interest is the x value itself, which is x equals 2. And we need to find f of x plus h. F of x plus h is just 1 over x plus h. And let me go ahead and plug in. Let me delete this here. Let me go ahead and plug in my actual x value. So the limit as h approaches 0 of f of x, which is 2 plus h minus f of 2 divided by h. So we need to find these two expressions here. F of 2, we found that one earlier, it's just right there. And then f of 2 plus h is f of 2 plus h is equal to 1 over 2 plus h. F of 2 we found earlier, but I'll write it again, 1 over 2. So we just plug everything in. The limit as h approaches 0 of 1 over 2 plus h minus 1 over 2 divided by h. And then how do we simplify this? Well, we're going to simplify it in a very similar way as we did the first method. It's a complex fraction. So we'll multiply. This is how I prefer to do it. I think this is how the book does it as well. We'll multiply by the least common denominator on both the top and the bottom. And if you're experienced with these complex fractions, you might see that this is fairly complicated is going to be more complicated than the previous method. So we're going to multiply the least common denominator, which is 2 times 2 plus h. And we really should multiply it both on top and the bottom. We need to multiply it both on top and the bottom. So I kind of goofed in the previous solution. I really should have written, and let me write it in purple just to show that I'm making a change here. On the left-hand side, we should put a 2x in the denominator. I did multiply in both the top and bottom, but I only wrote it once, which is technically incorrect. So there I've written it twice, 2x over 2x. So back to the right-hand side, we're multiplying it on the top and bottom. As I said, I am a little bit constrained on time. So, I'll skip the details here and say, if we multiply this product here times this first term, the 2 plus h's cancel and we get 2. If we multiply this product times the second term, we get a minus. The 2's cancel and the 2 plus h remains. Now, it is very important that we put these parentheses or brackets here because what's being subtracted here is that entire 2 plus h, not just the 2. So that's a very common mistake that students make. And then on the bottom, I'm not going to multiply it out. I'm just going to leave it as 2 times h times 2 plus h. Generally, something will cancel. And so let's continue. We have the limit as h approaches 0 of, let me write it actually up above so I can do this small simplification here. If I distribute this negative, we get in the numerator 2 minus h over 2h times 2 plus h. 2 minus 2, of course, those two would cancel. And so we get negative h, or the opposite of h, 2 times h times 2 plus h. These h's can cancel as well. So I'll cancel them. And we have the limit as h approaches 0 of negative 1 over 2 times 2 plus h. Now we can take the limit as h approaches 0. If you take a close look here, you know, in just the previous step here, you could not have taken the limit as h approached 0 because both the numerator and denominator would have gone to 0, making us, you know, giving us a limit 0 over 0, which is indeterminate. So now that we've canceled that h, we can, you know, let h go to 0, essentially just plug in 0 for h, and we get -1 over 2 times 2 plus 0. This is -1 over 2 times 2, which is 4. So the slope of the tangent line is equal to -1 over 4. And notice we actually finished on the exact same line as before. So which of these two methods is more complicated? I think the right-hand side was more complicated this time. You know, but you choose whichever one you like. And really, you should be able to do both. So, you know, when you're doing problems, maybe alternate between the two. All right, let's continue. And here's the, you know, here's the tangent line. So you can just see another example. The line just grazes the function at that point. Oops, you know, it's a little off there. But it just kind of barely touches it at that point. 2 1/2, yeah. All right. So the derivative of a function at a point. The type of limit we compute in order to find the slope of the tangent line to a function at a point occurs in many applications across many disciplines. These applications include velocity and acceleration in physics, marginal profit functions in business, and growth rates in biology. This limit occurs so frequently that we give this value a special name, the derivative. The process of finding a derivative is called differentiation. Okay, so here we're defining a new term, and it's something that we've already practiced, but we say that so okay, let f of x be a function defined in an open interval containing a. The derivative of the function f of x at a, denoted by f prime of a, it's f with a little apostrophe of a, is defined as this limit here. This is that limit that finds you the slope of the tangent line. So alternatively, we can also define it, you know, with the limit as h approaches 0. Okay, so when we say the derivative of f of x at 2, we mean the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Yeah, so we're given this limit. It's so important that we're giving it a special name. Okay. So estimating a derivative. Let's see what this says. For f of x equals x squared, use a table to estimate f prime of 3. So remember that so it says use estimate. We want to estimate f prime of 3. Well, what this is actually equal to, according to the previous definition, is this is equal to the limit as x approaches 3 of f of x minus f of 3 divided by x minus 3. And if we simplify this, we are looking at the limit as x approaches 3 of x squared minus 3 squared, or 9, over x minus 3. And so what this table gives us here is it gives us a couple of x values. Notice that this value is less than 3, but then the next value is getting closer to 3 and closer to 3. And the second column gives us the value of this quotient here. And so what value is this getting closer to? It starts at 5.9, gets closer to some value, 5.99, 5.999. It looks like it's getting closer to 6, right? So the limit from the left seems to be 6. The limit from the right, if you go above 3 and decrease, get closer and closer to 3, the values of that difference quotient are 6.1, 6.01, and 6.001. These seem to be getting closer and closer to 6 as well. And so after examining the table, we see that a good estimate for f prime of 3 is 6. Okay, That's nice, I guess. Yeah, that's all right. All right, so finding a derivative. This is probably the last example here that I'll do before calling it the end of the video. We'll see, depending on how long it takes. So it says, finding a derivative. Find f prime of 2. Okay, well, we just defined what f prime of 2 means in a previous definition, the previous definition. It is just equal to the limit as x approaches this value, 2, of the function f of x minus f of 2 divided by x minus 2. And this one's going to take a little bit more work here, just slightly more work. Yeah, so what is f of x? I'll write it up above. F of x is 3x squared minus 4x plus 1. Not too bad. But f of 2, we should kind of do this as scratch work and just plug in the 2 over here on the side. Simplify here. 3 times 4 is 12. 12 minus 8 and plus 1. This is 5. So f of 2 is 5, and we'll make our substitutions. The limit as x approaches 2 of the function f of x, that is 3x squared minus 4x plus 1, minus f of 2 is 5, divided by x minus 2. So let's continue here. We'll simplify a little bit if we can. The limit as x approaches 2 of, what do we get here? 3x squared minus 4x, and then plus 1 minus 5 gives us a minus 4, right? Divided by x minus 2. We're going to have to factor this numerator here. So I'll factor this, on the side over here. 3 times negative 4 is negative 12. So I need to think of two numbers that multiply to negative 12 and add up to negative 4. This is algebra here, so I'm not going to explain everything here, but if you have questions on this, feel free to leave a comment. Or two numbers that multiply to negative 12 are negative 6 and positive 2, and they add up to negative 4. So our factorization, let's see, x minus 6, x plus 2, and then since the leading coefficient was 3, no. Since the leading coefficient was 3, why is it doing that? That's weird. Okay, I don't know. Since the leading coefficient was 3, I'll divide both these by 3. If it reduces, then I get x minus 2. I reduce. If it doesn't reduce, I put this 3 in front of the x, and I get 3x plus 2. And so my factorization, or after factorization, I get x minus 2 times 3x plus 2 divided by x minus 2. Nice. I'm going to be able to cross out the x minus 2's, and so I get the limit as x approaches 2 of 3x plus 2. Now I can do direct substitution. So this is equal to 3 times 2 plus 2. This is 6 plus 2, or 8. And so the slope of the tangent line at x equals 2 is equal to 8, but we also now have called this the derivative of f at 2 is 8. Okay, so those are the same thing. The derivative of f of x at a equals 2 is the same thing as the slope of the tangent line at x equals 2. All right, let's see, do they give us a picture? No, they do it the other way, using the other formulation for the derivative, which is nice. It gives us the exact same, excuse me, the exact same answer. Now, I would argue, I don't have time to do it, unfortunately, but I would argue that this is probably more complicated, to find, just slightly more complicated. So again, you do need to know how to do it, or you should know how to use this other formulation, but yeah, so you can read that there. All right, let's see. And then we have just one more. I wish I had a little bit more time. Let's just quickly see what's going on here, what they say in this last section. Velocities and rates of change. Okay, now that we can evaluate a derivative, we can use it in velocity applications. Recall that if s of t is the position of an object moving along a coordinate axis, the average velocity of the object in the time interval from a to t, if t is greater than a, or from t to a, if t is less than a, is given by this formula here. Yeah, so we can find the average velocity over an interval by finding the position at the end of the interval, subtracting the position at the beginning of the interval, that's like y2 minus y1, divided by x2 minus x1, subtracting the time values. And this is going to give us the distance divided by the time. And we know distance divided by time gives us sometimes called the rate of change. Since this is rate of change of position, we call this the velocity. As the values of t approach a, the values of v average approach the value we call the instantaneous velocity at a. That is, instantaneous velocity at a, denoted v of a, the velocity at a, is just the derivative of the position function s at a, which is just going to be the limit as t approaches a of this difference quotient. To better understand the relationship between the average velocity and instantaneous velocity, see figure 3.8. In this figure, the slope of the tangent line, shown in red, is the instantaneous velocity of the object at time t equals a, whose position at time t is given by the function s of t. The slope of the secant line, shown in green, is the average velocity of the object over the interval from a to t. And so you can see the exact same idea here, just put in a position velocity context, is the position of this object is kind of changing, excuse me, and we have an approximation of the velocity, or we have an average velocity over this interval here, over these 2 points from a to t, and that slope tells us the average velocity over that time interval. But it would be a lot nicer if we could have the exact instantaneous velocity at the instant a, at the value a, t equals a, at the time a. And so, well, we can apply the same idea. Rather than finding the average velocity, we can shorten that interval, make t approach a, take the limit as t approaches a, and the slope of the secant line will approach the slope of the tangent line. And we can get the instantaneous velocity at that point. We can use equation 3.5 to calculate the instantaneous velocity, or we can estimate the velocity of the moving object by using a table of values. We can confirm the estimate by using equation 3.7. All right. All right, so we'll stop there. Yeah, and you know, maybe I'll make a second video to finish off this section. All right. Well, thanks for tuning in. Leave a like on the video, or you know, a comment or something, to let me know that you enjoyed the videos, and I'll just try to keep making them.